So let me show you the tutorial sheet if you haven't seen it already. So you share screen. Sorry. So the tutorial sheet is, let me close this. Is this one here, right? So if you click here, you will see the tutorial sheet for week 5. As usual, I will take you line by line, and there are 5 exercises at the end of the tutorial sheet. I will try to do as many of them as I can. Okay. All right. To start with, let me go to page 1. Page 1. Now, in R, one of the main features in R is that it has many distributions implemented in it, right? All the distribution that you will encounter in your lifetime, right, plus more, are implemented in R. So, as you know, there are 2 types of distributions. There are the discrete ones, and there are the continuous ones. Now, some of the discrete distributions implemented in R are the binomial, Poisson, etc. And some of the continuous distributions implemented in R are uniform, normal, exponential, etc. Right? Now, for every distribution, there's an abbreviation. For every distribution, there's an abbreviation in R. Right? So, for example, the binomial is abbreviated as BINOM. The Poisson is abbreviated as POIS. The geometric is abbreviated as GOM. The uniform is abbreviated as UNIF. Normal is abbreviated as NORM, and so on. Now, going down to the bottom of this, excuse me, going down to the bottom of this page. Now, for every distribution, you can compute the density or the CDF or the quantile or the random numbers. So that's the purpose of this dname, pname, qname, rname command. So if you have a distribution given by the name, so it could be norm, it could be unif, it could be poise or anything, and you want to suppose you, excuse me, dname will compute the density function. So if it is discrete, it will compute the probability mass function. Pname will compute the CDF. Qname will compute the quantile, and rname will compute the random numbers associated with the distribution. So, for example, if you take norm, as you saw in the earlier table, norm stands for normal distribution. So dnorm will compute the density of the normal. Pnorm will compute the CDF, or the cumulative distribution function of the normal. Qnorm will compute the quantiles associated with the normal. Rnorm will generate random numbers from normal. All right. So these 4 names, D, P, Q, R, apply to any distribution. It could be normal, it could be exponential, it could be log normal, and so on, right? They apply to any distribution. All right, guys. All right, now let me go to the next page. Next page, that's where we start to use some commands. All right, so the first thing I'm going to do is I'm going to open R. I'm sure you guys know how to open R. So you go into Start menu, you go down this, and then you click here and choose the 64 version. So this is what you will get. All right. All right. The first thing I'm going to do is I'm going to show you how to draw the PMF of a binomial distribution. So I define X. Excuse me. I define X as a sequence of numbers from 0 to 50, right? And then I define Y as the density, or in this case, the probability mass function of the binomial remember, binomial has 2 parameters, the size parameter and the probability parameter. I'm going to take them to be 50 and 0.6. Then I say plot x comma y, and this is what I will get. So this is the plot of the PMF, or the probability mass function of the binomial. If you like, you can join the points together. To join the points together, you can use type equal to L. L stands for line. The L should not be confused with 1, right? It is L, not 1. So if you type, this is what you see. Now you get a smooth curve, right? So that's how you plot the density of a binomial. But now suppose you want to compute, okay, suppose x is binomial with parameters 50 and 0.6, right? And suppose you want to compute the probability that x equal to 35, right? Now in R, you can do this by using the dbinom command with 35, size equal to 50, and probability equal to 0.6. So this is what you will get. Okay. Now suppose you want to find the probability that x is less than or equal to, say, 25. In R, you can do this by using the command P. Remember, the P binom is used to denote the CDF, right? It used to compute the CDF. So here you're looking for the CDF at 25. So P binom in brackets 25 will compute the CDF at 25, okay? But now suppose you want to find the probability that x is between, say, 20 and 30, right? Now, because x is a discrete random variable, you can write this as the difference of these two probabilities. All right. Okay. So to compute, in order to compute this, you will use you will first compute P binom at 30 and take away from that P binom at 19. All right. So this is the probability that x is between 20 and 30. As usual, if you have any questions, guys, please feel free to use the chat room, right? Okay. So please feel free to, don't be afraid. I'm here to help you guys. Okay. All right. Now, suppose you want to find the quantile of a binomial distribution. You use the command qbinom, right? So suppose you want to find the median, which corresponds to the 50th percentile, with size equal to 50 and probability equal to 0.6. So this is the median. And suppose you want to find the first quartile, which is corresponds to 25th percentile, is this. Suppose you want to find the third quartile, which is the 75th percentile, is this, right? Okay, now finally, suppose you want to generate random numbers. Suppose you want to generate random numbers of size 5 from the binomial distribution. This is what you use the command rbinom. So rbinom will generate random numbers from a binomial of size 5 from a binomial distribution with parameters 50 and 0.6. So these random numbers, these 5 of them, come from a binomial distribution with parameters 50 and 0.6. Now, every time you repeat, you get different numbers because they are random, right? So every time you generate numbers, they will be different. They may not be the same exactly, right? All right, guys, any questions so far? You okay? Guys, talk to me. Are you okay so far? If you have questions, just please feel free to talk to me, okay? Okay, thank you, guys. All right. All right. Next, The next thing I'm going to talk about is so far I talked about the binomial, which is a discrete distribution. The next thing I'm going to talk about is the continuous distribution, which is the normal. Obviously, the normal is the most popular continuous distribution. Now, suppose you want to compute the density of a normal, right? Then you will use the command denorm. So this command here will compute. It computes the PDF of n01 at x equal to 0. So basically, when you don't specify the parameters, the R automatically assumes what you're computing is the density of a standard normal, that is mean 0 and variance 1. And you're computing here the density at x equal to 0. Now, suppose you want to compute the density at different values. Say mean equal to 10, and mean equal to 4, and standard deviation equal to 10. This is what you will get. So what you did here is the PDF. You computed the PDF of a normal distribution with mean 10 and variance 10 squared at x equal to 10. So that's what you did right now. All right. So you computed the PDF of a normal with parameters 4 and 10 squared at x equal to 10, x equal to 0, right? So just to make it clear, guys, when you don't specify mean or SD, R will take them to be 0 and 1 respectively, right? But if you want it not to be the standard normal, then you need to specify the mean and SD for standard deviation, right? Okay, guys, is that clear? Yeah. So, right. The next thing is I'm going to show you how to draw the PDF of a normal distribution, right? So let me define the x-axis first, and let me define y to be denorm at x, say with mean equal to 4, standard deviation is 10, and then I say plot x comma y. And as you can see here, this is a typical shape of a density of a normal distribution. If you want, you can join the points by line, and you will get this smooth version, right? This is a smooth version of the density of a normal, okay? Now, suppose you want to compute the probability that x is less than or equal to 4 when x is normal with parameters 4 and 10 squared, right? To do this, you use the command p normal at 4, mean equal to 4, SD equal to 10. So this is how you compute the CDF of the normal at 4 with these parameters for the mean and SD, right? And you can also do this for multiple values of x. So for example, this will give you 3 values. So the first is the probability that x is less than or equal to 4. The second is the probability that x is less than or equal to 8. And the third is the probability that x is less than or equal to 12, right? And you can compute Q norm. So Q norm will compute the quantiles of a normal distribution. So if you say Q norm at 0.975, that's the quantile of a standard normal at p equal to 0.975. So if you say this is the quantile of a normal with parameters 4 and standard deviation 10, right? And this is the median of the normal with parameters mean equal to 4 and standard deviation equal to 10. And this is the first quartile of a normal with parameters 4 and 10. and this is the third quartile of a normal with parameters 4 and 10. All right, and so on. All right, next is, suppose you want to generate random numbers. So you use the command rnorm. Rnorm stands for generate random numbers from a normal distribution. So the first parameter here is 5, denotes the number of how many random numbers you want to generate. So in this case is 5, and mean and SD are the parameters. So this is what you will get. So these 5 numbers come from a IID and come from a normal distribution with mean equal to 4 and standard deviation equal to 10. And every time you repeat, you get different numbers because they are random, right? All right, guys. All right, the next thing, are you okay so far? Okay, the next thing I'm going to show you is I'm going to show you how to draw a histogram and how to plot the PDF on top of the histogram. To do that, let me simulate some data, right? So I'm going to simulate the data from a gamma distribution. I mean, you might have talked about the gamma distribution in probability 1 last semester. So what I have done here is I have simulated 100 random numbers from a gamma distribution with parameters 200 and 2. The shape parameter is 200 and the scale parameter is 2. The next thing I'm going to do is I'm going to draw a histogram of the simulated data with frequency equal to, remember frequency equal to f means that I'm going to use the density scale for plotting the histogram. And xlim specify the limits for the y-axis. Okay, and also let me put breaks to be 11. So this is what you get. You see what I've done. This is what I have drawn here is the density of a simulated data from gamma distribution with the y-axis in the density scale, and the x-axis goes from 280 to 500. So that's what xlim means. Xlim basically means limits of the x-axis. Goes from 280 to 500, and breaks equal to 11 is just how many breaks you want you want 11 bars. So that's what it means, right? Now what I'm going to do is I'm going to plot on top of this histogram the density of the gamma distribution. So let me first define the sequence from 280 to 500 in steps of say 0.1, right? And then define y to be the density of the gamma, right, at x with shape parameter 200 and scale parameter 2. All right, then I will use the lines command, right? And this is what you will get. You see what, as you can see, the density of the gamma distribution that I have plotted in black matches up the histogram pretty well, as you would expect, because the histogram is that of the simulated data from a gamma distribution. Hence, if you plot on top of it the density of the gamma, right, that you simulated from, it must match this. It must match the histogram pretty well, as you see here, right? Okay, so it's not a surprise. All right, now what I'm going to do is I'm going to plot another density of another distribution, namely the density of the normal distribution, with the mean given by the mean of the simulated data, and SD given by the standard deviation of the simulated data, right? Okay, and I'm going to draw this with line type equal LTY. By the way, LTY stands for line type, right? And let me use a different color also, say red. And this is what you see. So now you see there are two curves. The one in black is the density of the gamma distribution, and the one in red is the density of the normal distribution. As you can see, both of them are pretty close to each other. That means the normal is a good approximation to the gamma in this particular case.
Lasagna for breakfast.
Hello, guys. Can you keep quiet, please? I'm talking, guys. So sorry. Sorry. So as you can see, do you follow this example, guys, or not? In this example, I mean, you have questions in this example. In this example, okay, let me summarize one more time. In this example, I simulated data from gamma, all right, with certain parameters. And then on top of the histogram of the simulated data, I plotted the density of a gamma, right? The same gamma that I simulated from. And then finally, I plotted on top of that also the density of a normal, right? With the parameters taken to be the mean and the standard deviation of the normal. And as you can see, the normal distribution is a good approximation to the gamma distribution, right? Okay, in this particular case, but it may not be true in general, right? In general, it may not be true, but for this particular data that we just simulated, the normal is a good approximation by looking at this picture here, right? But in general, it may not be the case. Now, to illustrate that point, let me show you. In general, the normal is not a good approximation to the simulated data. Now, to illustrate that point, let me show you what I'm. Okay, let me simulate. Let me simulate a sample of size 100 from an exponential distribution, right? Okay, then you should do a histogram of this data with frequency equal to f. It will look something like this, right? So as you can see, the x-axis goes from 0 to 7, and the y-axis is in the density scale. So let me take the limits for the x-axis to go from 0 to 7, as I just mentioned. And let me define x to be a sequence from 0 to 7, say in steps of 0.1. And let me define y to be the density of the exponential at x with rate parameter equal to 1. Then if you do lines x comma y with line type equal to 1, this is what you will get. As you can see, the density of the exponential, right, fits the histogram pretty well, as you would expect, because the histogram was simulated from an exponential distribution with rate parameter equal to 1. Now let me compute y also as the density of at x with the mean parameter equal to the mean of the simulated data, right? And the SD parameter equal to the SD of the simulated data. Now, if you plot the density of the normal on top of the density of the exponential with a different color, say red, right? This is what you will see. You see, now in this example, the normal density, which is in red, is not a good approximation to the data, right? Because as I said in the last example, in the previous example, right, the normal is always not a good approximation to the data. In some cases it is, in some cases it is not, But in this example, it is not, as you can see, right? The normal is not a good approximation, right? So I just wanted to illustrate this. All right, guys, any questions? Any questions before I do there are 5 exercises at the very end of the tutorial sheet. I'm gonna start doing them in a sec. Before that, let me see if you have any questions, guys, please. Are you guys okay or what? Hello, guys. Talk to me, please. Okay, thank you. All right, so let me. All right, okay, that's a good question from Neil. Yeah, lines, like if you want to plot something on top of something, like here, guys, you have the histogram, right? And you want to plot something on top of the histogram, you have to use the lines command, right? If you use the plot command instead, like if you use the plot instead of line, then it will override what is already in the picture, in the window, right? You don't want to do that. You want to plot something on top of the histogram. So in order to do that, you need to use the lines command, not plot, right? And if you use plot, it will override what is already on the in the window, right? And obviously, you don't want that, right? All right. Any other question, guys? Is that okay, Neil? Yeah. I hope you got what I said. Any other questions, guys? You want to know? You okay, guys? Just talk to me, guys. Sure. All right. Okay. So let me start with exercise 1. Exercise 1. All right. Here you have x is a binomial distribution with parameters 100 and 0.3. So the size parameter is 100 and the probability parameter is 0.3. And we want to compute the probability that x is equal to 33. Now to do this, you will use the command binom, right? At 33, the size parameter is 100 and the probability parameter is 0.3. That's easy, right? Okay. All right, the next part is asking you to find the probability that x is between 28 and 34. Now to do this, because x is a discrete variable in this case, you have to write this as like this, right? Remember, x can only take integer values. So this probability is this, take away this, right? All right, so to compute the probability that x is less than or equal to 34, use binom at 34. Take away binom at 27, size equal to 100, the probability equal to 0.3. Right, this is what you get. All right, next, you want the probability that x is less than 38. All right, now if x is less than 38, that's the same as saying that x is less than or equal to 37, right? Because x can only take integer values. So this you can compute using binom at 37, size equal to 100, probability equal to 0.3. All right, so this completes part 1 of question 1. Part 2 is about normal approximation, which I did not cover in the course, so I will skip it. I will not ask you anything to do with, I will not ask you any question to do with the normal approximation, so don't worry. So let me move on to part exercise 2, unless you have questions on exercise 1. Are you guys okay with exercise 1? Before I move to exercise 2. Hello. Hello, guys. Are you okay with exercise 1? Okay, thank you. Okay, let me go to exercise 2. So in this case, x is a Poisson variable, is a Poisson random variable with parameter 10, right? The first thing is to draw the plot of the PMF over the range 0 to 25. So you define x from 0 to 25 in steps of 1. So you see these are the numbers you get. And you define y as the density of the Poisson at x with lambda equal to 10. And you plot x comma y. This is what you get, right? So what I have drawn here is the density of a Poisson variable with lambda equal to 10. If you like, you can join the points, right? And this is what you get. So type equal to L. L stands for line, right? Okay, guys. All right. In part 1, we also want to find the probability that x is less than 15. Now, Poisson is also integer valued random variable. So this is the probability that x is less than or equal to 14, right? So to compute this, you use P Poisson at 14, lambda equal to 10. We also want to find the probability that x is greater than or equal to 8, right? And this you can write as 1 minus the probability that x is less than 8, right? And this is, you can write as 1 minus the probability that x is less than or equal to 7, right? So this is 1 minus P Poisson at 7, lambda equal to 10. Next, we want to find the probability that x is between 6, 16, right? Right, which is, right, this you can write as the probability that the difference between the probability that x is less than or equal to 16 and x is less than or equal to 5, right? Right, remember, the probability between 6 and 16 is the difference of the probabilities at 16 and 5, all right? So this is gonna be P Poisson at 16, lambda equal to 10, P Poisson at 5, lambda equal to 10. All right, so that completes part 1 of exercise 2. Part 2 is asking you to find the low quartile, median, and the upper quartile. All right, to find the lower quartile, you use the Q Poisson command with probability 0.25. So this is the, sorry, excuse me. I made a mistake. It should be 10, not 100. So this is the low quartile of a Poisson variable with lambda equal to 10. And this is the median of a Poisson variable with lambda 10. And this is the third quartile or the upper quartile of a Poisson variable with lambda 10. All right, guys, so that completes exercise 2. You okay with that? Guys, are you okay? All right, let's move on to exercise number 3. Exercise number 3 is about the exponential distribution, right? So here we are assuming that x is exponentially distributed with parameter 0.2. The first thing we want is to plot the density of the exponential. So let's define x to be, say, sequence from 0 to 25, say in steps of 0.1, and define y to be the density of the exponential at x with parameter 0.2, and then you say plot x comma y, and this is what you will get. So what I have drawn here is the density of an exponential with parameter 0.2. And as before, you can join up the points using type equal to L. This is what you will get, right? All right, the next thing we want to do is we want to find the probability that x is less than 12. All right, now this, because remember, for a continuous variable, because x is exponential, right? X less than something is the same as x less than or equal to something, right? It doesn't make a difference. And similarly, x greater than something is the same as saying x is greater than or equal to. So the probability that x is less than 12 is the same as the probability that x is less than or equal to 12, which is px at 12 with parameter 0.2, right? And the next, we want to find the probability that x is greater than 3, which you can write as 1 minus the probability that x is less than or equal to 3. So this is 1 minus px at 3, parameter 0.2. Next, we want to find the probability that x is between 4 and 20, and this you can write as the probability that x is less than 20, take away the probability that x is less than or equal to 4. All right, so this will be in R, this will be px at 20 minus px at 4. All right, guys. Okay, and the next part is to, where am I? I'm running out of pages here. Okay, I'm trying to find the next part of the question here, guys. Is it here or not here? What is the next part of the question? Here we are. Okay, the next part of the question is to find the 20th, 50th, and 80th percentile. So to find the 20th percentile, use the QEXP command with probability 0.2, right? So this is the 20th percentile of an exponential distribution with parameter 0.2, right? And this is the 50th percentile, or the median, right? And this is the 80th percentile of an exponential, right, with parameter 0.2. All right, guys. So that completes exercise 3. Exercise 3. Are you okay with that or no? Before I do the next exercise, if you're okay with this, okay, let me move on to exercise 4 now. Exercise 4, here we are assuming that x is normal with parameter, the mean parameter equal to 20 and the variance parameter 7 squared, right? And the first part is asking you to plot the PDF, so over the range 0 to 40. So let's define x to be a sequence from 0 to 40 in steps of, say, 0.5, and y as the density of the normal at x with the mean parameter equal to 20 and the standard deviation parameter equal to 7. Then you say plot x comma y. This is, so what you see here is a typical shape of a density of a normal distribution. In this case, with mean parameter 20 and the standard deviation parameter 7. If you like, you can join the points together using L. This is what you get, right? Okay, guys. All right. The next thing we want to do is to find the probability that x is less than 17. Right. To find this, you use the command pnorm at 17 with the mean equal to 20 and standard deviation equal to 7. Now, once again, as I mentioned in the previous exercise, x less than is the same as x less than or equals to, right? So it doesn't make a difference, right? All right, the next, we want to find the probability that x is greater than 25. Now this you can write as 1 minus the probability that x is less than or equal to 25. All right, so this is 1 minus p norm at 25, mean equal to 20, and standard deviation is 7. Okay, so this is the probability. All right, next we want to find the probability that x is between 13 and 27. All right, now this you can write as the probability that x is less than 27 minus the probability that x is less than or equal to 13. All right, now you should do the in R. You can compute this like p norm at 27, mean equal to 20, and standard deviation 7. At p norm at 13, mean equal to 20, and standard deviation is 7. So this is what you get. All right, guys. All right, so that's easy. All right, the second part of question 4 is to find the 5th, 10th, 90th, and 95th percentiles. All right, so let me show you. To find the percentiles, you use the command qnorm. So to find the 5th percentile, you say 0.05 with mean equal to 20 and standard deviation 7. So this is the 5th percentile of a normal distribution with parameter with mean equal to 20, standard deviation equal to 7. And this is the 10th percentile, and this is the 90th percentile, and this is the 95th percentile. All right, we just changed the first argument, right, to whatever you want, all right, any probability. How do you copy command? I don't copy, I just use the arrow key, man. Just use the arrow key to go up or above. Just use the arrow key, right? All right, okay, so that's the second part. Now, to part 3 of exercise 4 is asking you to compute the percentiles using a different approach. Now, I don't know if I told you in the class or not, but if you have a variable x that is normal with parameters mu and sigma squared, right, then the quantile function q of p of x is the same as mu plus sigma times the q of p of the standard normal. Did I mention this in the class? Maybe not. I don't know. If I did not, I'm sorry, but this is it's a useful property to know that what I have written. Okay, if x is a normal variable with parameters mu and sigma squared, then the quantile function of x, right, this q of p of x is the same as this. That is mu plus sigma times q of p of the standard normal, right? So now let me illustrate this, right? So let's go back to this here. This is the quantile at 0.05 of a normal variable with these parameters, right? Now I'm going to show you how to compute this using this formula here, right? So that will be mean is 20, right? Your mu is 20, your sigma is 7, right? Times q norm at 0.05. Now, as I mentioned before, guys, if I don't put the mean on ST, R assumes that the mean equal to 0 and ST equal to 1. So as you can see, this value here is the same as this, right? Because of what I just said, the formula that I just gave you, right? Right. This is the same as this, right? And similarly, for the 10th percentile, you get 11.025, which is the same as this. And for the 90th percentile, you get 28.97, etc., and the same as this, right? And for the 95th percentile, you get 31.513, etc., which is the same as this. All right, so what I have just explained to you is the fact that there are two ways to compute the percentile of a normal. One way is to use the qnorm command with the given mean and the given standard deviation. And another way is to use this formula here, right? That is the formula where mu is the mean, S sigma is the standard deviation of the given variable, times the quantile function of the standard normal, right? All right, so there are two ways of doing it, all right? So that completes exercise 4. Are you guys okay with that? You have questions? Any questions on exercise 4, guys? Hello, guys. Talk to me. All right, there's one more exercise left, which is exercise 5. Right. Do you, I don't think I have the time to complete it, but anyway, I will try to do the first part. So let me show you. Okay, let me go to exercise. Let me show you. I think you have the sheet in front of you, don't you? So this is exercise 5. Exercise 5 is this one here. So the first part is to do a histogram of the simulated data, and on top of the histogram, plot the PDF of the normal with parameters 10 and variance equal to 4. It shouldn't be too difficult to do, right? So the first thing you need to do is, right, let me show, is to read the data. This is the simulated data. I think I mentioned this before. So you copy the data, and so this is exercise 5, guys. Okay, exercise 5. So I'm going to read this data with header equal to true. Let me call this sim data read dot table, right? Okay. There's something I made a mistake. Sorry. Control Z. I forgot to close the. All right. Okay. Now I have read the data. This is the data that I just read. Now I want the second column, which is this. So I want to do a histogram of the second column with frequency equal to f, right? And this is what you will get, right? This is the density of the histogram of the data, right? Now let me take the x-axis to go from 6 to 16. So I'm going to say the x lim to be from 6 to 16, right? Now I'm going to define x as a sequence from 6 to 16, say in steps of say 0.1, right? And y as the density of the normal distribution with parameter at x with mean equal to 10 and the standard deviation equal to 2, right? Okay, now if I use the lines command, x comma y with line type equal to 1, this is what I've got. So as you can see, the normal distribution with parameters 10 and standard deviation 2 is a good approximation to the density of the data, right? So that's the first part of exercise 5. Second part is to repeat the same thing for the Giza data, right? But I'm unfortunately sorry. I got a question here. How do you deduce the normal distribution? I don't understand. What do you mean? Do you need to specify the size of the normal distribution? No, you don't need to, sir. You don't need to specify the size. The size is 100 is the size of the simulated data. You don't need to specify that, Neil, because 100 is how many data points you have. And I used the hist command to do a histogram of the simulated data, which is here. How do you know that mean is 10, SD is 2? That's because it's given in the question, Mikhail. You should read the question, Mikhail. It says the random sample is from a normal distribution with parameters 10 and variance 4. Mikhail, did you read the question, part 1? Just go to part 1. Okay, let me show you. Maybe you have it on your laptop, right? Don't you? Okay, let me show you. You should go to the tutorial sheet, right? You should go to the tutorial sheet on page. It says here. You see, it says that data is from a normal distribution with parameters 10 and variance 4. All right, guys. So I have done only the first part of exercise 5, but part 2 and part 3 are similar, so you should be able to do them by yourself. But anyway, I will post all the solutions online tomorrow. So tomorrow, Wednesday, I will post all the solutions to all the questions tomorrow in the course website, so you'll be able to see them. You should have problems doing these 2 parts, right? All right, guys. So any other questions you want to ask? Okay, just let me remind you guys, the quiz 4 is due on Thursday this week, right? So if you haven't done it, can you please complete it by Thursday 10 a.m., right? Otherwise, have a good morning or good afternoon or good evening. I will talk to you soon. And any problems, please feel free to contact me 24/7 by email, Skype, Zoom, or phone. My home phone number is 0161 273 2941. All right. Take care, guys, wherever you are. All right. Good talking to you.